For this video, I'm going to start with a little demonstration. Let's take a 9-volt battery and some copper wires and connect the battery to a pair of metal plates. Electricity flows from the battery and charges begin to build up on the plates, since they can't jump through the air between the plates. This leads to one plate becoming positively charged and the other negatively charged. The difference in charge between the plates creates a field, represented by the blue arrows. This is what we call an electric field, and now I'm going to explain what it does and what you need to know about it. Let's have a closer look at those metal plates. If one of them builds up with positive charges and the other with negative charges, then an electric field exists between them. The strength of this field can be measured, and we denote it with a capital E. The arrows show the direction of the field, and by convention, it goes from positive to negative. Any charged particle inserted between the plates will move relative to this field. You can also see that their arrows are evenly spaced, all the same distance apart. This represents a uniform field, one which has the same strength everywhere. That means that the force on a charged particle is the same no matter where you put it. If we drop a positively charged particle in between these plates, its path will be bent by an electric force. As you can see, it curves toward the negative plate. Why is this? It just follows the field lines, which go from positive to negative. Remember, like charges repel, so you'd expect a positive charge to move away from the positive plate. Opposite charges attract, so it ends up sticking to the negative plate. That's the conventional way, but in electricity we tend to think more about electrons, which are negatively charged. Dropping an electron into the field, we see that its path curves in the opposite direction. It's going against the field lines. If you like, you can take the whole field and flip it around, so it becomes negative E. This field goes across from negative to positive and shows you which way an electron will travel. Just keep in mind the elementary rules. Like charges repel and opposite charges attract. This is the underlying principle behind an electric field. As a direct result, positive charges will move in the opposite direction to negative charges like electrons. We have some handy formulae to put numbers on the field. The strength of the field between those plates, capital E, is given by the voltage between them divided by the separation distance, that is, how far apart they are. The force on a charged particle can also be calculated. It's the field strength times the size of the charge in coulombs. Let's look at that first formula in more detail. Electric field strength is voltage divided by a distance, so we measure it in volts per meter. That implies that you have two ways to increase the strength of the electric field. First, you can increase the voltage between the two plates. Do this by using a bigger battery with more juice, but be careful not to make it too much voltage. You could also bring the plates closer together, reducing the distance between them. What have we learned so far? Well, it turns out that a charge difference creates an area called an electric field. This field can be characterized by the voltage divided by the distance across the field. E equals V over D. The function of an electric field is to produce an electric force, which affects the motion of any charged particle inside the field. If the field is uniform, the position of that particle doesn't change the size of the force acting on it. The most important thing to remember is that electrons move against the field. By convention, field lines go from positive to negative. You have Benjamin Franklin to thank for that. Electrons travel the other way, as they are attracted to positive charges like a cat to a stranger's leg. There's one more thing to explain. This equation appears on your formula sheet, and I don't want you to be misled by it. Notice there are two capital E's. Only one of them stands for electric field strength. The first E refers to energy, specifically the potential energy of a particle. This energy is given by the field strength times the size of the charge times the distance it travels in an electric field. It means that a charged particle will gain or lose electrical potential energy when it moves through the field. The field does physical work on the particle in order to generate the force that gets it to move in the first place. It's a weird and wonderful concept, but we're starting to make some sense of electricity. In the following exercises, you will become more familiar with fields, charges, and calculations involving static electricity. If you feel unsure about anything, come back and watch this video again. Thanks for watching.